Hi friends, good morning. Welcome back to another session, the design of steel structures. So in the previous class, we have discussed regarding the introduction to the design of tension members. We have seen what are the different forms of tension members, where applications of tension members. Next, we'll have seen some keywords like shear lag, gross area, net area. Okay, and we have seen the maximum slenderness ratio values, and from the code we have seen the different modes of failures of tension members, that is the design of tension members. And one problem we have solved. Today we'll try to solve some more problems. Okay, so first problem we'll take here is, first we'll start with the small 3 marks problems, later on we'll go for the essay type. So what is today's first question is, calculate the design strength of tension member of a tension member due to yielding of cross section, yielding of cross section of ISA 100 by 65 by 10 mm. Take Fi as 250 MPa. This is the question, very small question it is. So for given ISA 100 by 65 by 10 mm, from steel table you are supposed to take the gross area. If steel table is not available, then you can calculate easily. That is AG equals to 100 minus 10 by 2 into 10 plus 65 minus 10 by 2 into 10. Okay, so 10 by 2 means 95. It will be 950 plus 65 minus 10 by 2 means 60 into 10, 600. So overall it will be 1550 mm square. Okay, next, as per yielding of cross sectional area, so TDG equals to AG Fy by gamma m naught. Now what is AG? 1550 into Fy 250 divided by gamma m naught due to yielding is 1.10. Okay, so 1550 into 250 divided by, okay, it is 352.27 into 10 power 3 newtons. Okay, this is the question. Okay, very easy, right? Next, one more problem we'll try to solve. Calculate the design tensile strength of a plate. Here it is given as plate in rupture, means TDN. If it is connected to a gusset plate by welding. The plate is 300 by 10 mm. Take Fu as 410 Newton per mm square and Fy as 250 MPa. This is the data given. Okay. Now from the code book, TDN. This is for what? Plates. TDN equals to 0.9 AN Fu by gamma M1. Now AN is net area. Since it is welded connections, gross area will be equals to net area. Okay, gross area will be equals to net area. Right. Now what is the gross area of the plate? Simple thing, it is 300 into 10, that is 3000 mm square. This is the area. Next, now under AN you got 3000. Fu already given. What is gamma M1? For rupture, gamma M1 equals to what? 1.25. 1.25. Okay. Now TDN equals to 0.9 into 3000 into 410 divided by 1.25. Okay. So 0.9 into 3000 into 410 divided by, so how much you are getting? 885.6 kilonewtons. This is one more small problem. Next we'll see another essay type question now. One second. So next problem is a single angle ISA 200 by 100 by 15 mm is connected to a gusset plate of 12 mm thick by fillet welded of 8 mm size with its what? Longer leg. Okay. Determine the design tensile strength. Here they are not specially mentioned regarding the only yielding due to rupture or block shear. They have not mentioned. They are asking what is the design tensile strength of the tension member with Fy 300 MPa or Newton per mm square and Fu 440 MPa. Effective length of weld is 240 mm. Okay. Now given data. Now here, when you are calculating design strength, tensile strength of a tension member, you have to calculate for three values. What is strength due to yielding, strength due to rupture, strength due to block shear. These are the three values you have to do. Okay. So what is this given data? ISA 200 by 100 by 15 mm. This is the value given, right? First, we'll check with respect to what? Design strength due to gross section yielding. Gross section yielding of gross section. Okay, or gross section yielding, whatever it may be. Both are same. First, you write formula, that is TDG equals to AG F5 by gamma naught. AG. What is this AG you have to calculate? Now, if it is from the steel table, it is well and good, but AG 200 minus 15 by 2 into 15 plus what is another one? 100 minus 15 by 2 into 15. Okay, so you will be getting around 15 by 2. Okay, 200 minus 7.5 plus 100 minus 7.5 into 15. So 4275 mm square area it is, right? Mm square. Now substitute here AG 4275 into what is Fi is given as 300. What is yielding? 1.10, right? So into 300 divided by 1.10. So you will be getting around 1165.909. 1165.909 kilonewtons. Okay, this is due to cross section yielding. The second one is design strength due to net section rupture. Now TDN formula equals to 0.9 ANC FU by gamma M1 plus beta into AGO F5 by gamma M0. This is the formula. Okay. Now we'll solve net area, gross area, right? What is this ANC? ANC is what? Area of connected leg. Means which leg is connected? Longer leg is connected. So 200 minus 15 by 2 into 15. Okay. So 200 minus 15 by 2 means 1.5 into 15. How much it is? 288 1.5 mm square. Okay. Next AGO, gross area of outstanding leg it is. So 100 minus 15 by 2 into 15. So 100 minus 7.5 into 15. So how much here? 1387.5 mm square. Right. Next, what is required? Beta. What is beta value? All these are yesterday we have discussed, right? So that is 1.4 minus 0.076 W by T into F5 by Fu and BS by LC. Okay. Now if I substitute beta equals to 1.4 minus 0.076 into, what is the formula? W, once again I will write here, W by T into Fi by Fu into Bs by Lc. Now 1.4 minus 0.076 into outstanding leg, how much it is? 100 by thickness of the member is 15 into Fi is given as what? 300 MPa by 440 MPa into, for a welded connections, W will be equals to Bs, that is, yesterday I have shown you one diagram also in your IS 800 2007, that is 100, and the weld length of effective length of weld is given as 240. Now if I solve this, how to solve this? 100 divided by 15 into, close the bracket, 300 by 440, next 100 by 240 into, so how much you are getting? 1.256. This should not be less than 0.7, so it is greater than 0.7. Okay, but it has to be minimum, right? Beta max is how much? That is Fu gamma m naught by Fi gamma m1. What is Fu? 440 into 1.10 divided by 300 into 1.25, right? So 440 into divided by, so 1.29. Okay, means beta value should be in between 0.7 to 1.29. It is 1.256, hence it is okay, valid. Okay, now substitute here in TDN. What is this TDN? 0.9 into ANC Fu by gamma m1 plus beta into AGO into Fi by gamma m1, sorry, m0. This is the formula, right? So here 0.9 into, you got as to some 2885, right? 2887.5 into 440 divided by 1.25 rupture, right? Plus beta 1.256 into, what is this area got? 1387.5 into 300 divided by gamma m naught is 1.10. If I solve this, 0.9 into 2887.5 into 440 divided by 1.25, so 914.76 kilonewtons plus this one 1.256 into 1387.5 into 300 divided by 1.10. So how much you are getting? 475.28. Okay, so 914.76 plus 475.28, how much it is? 1390.04 kilonewtons. This is the total load due to rupture. And third one we'll see is design strength due to block shear. This is tau dB. Now first we'll write the formulas here. TdB1 equals to AVG F5 by root 3 into gamma m naught plus 0.9 into ATN FU by gamma m1. Next TdB2 equals to 0.9 AVN FU by root 3 gamma m1 plus ATG F5 by gamma m0. No need to worry, these values will be there, these formulas will be there in case of your code book, right? Now for that we'll try to do is what? Now if this is the angle section connected, total length of weld it is done. Okay, now this area will be under what? Tension, and this area will be under shear. Okay, now yesterday we have discussed area under what? Area under shear. You can write AVG or AVN, which is what? Length of weld into 2 times of thickness. What is length of weld? 240 into thickness 2 into 15. Okay, so how much it is? 15 to 30. 240 into 30. How much it is? 7200 mm square. Next, area under tension. Area under tension. What is the formula? This length, okay, multiplied with the thickness, right? What is this? 200 into 15, right? So 3000 mm square. Now substitute here TdB1. What is this TdB1? AVG means 7200 into Fy is 300 by root 3 into gamma m naught, it is 1.10 plus 0.9 into what is ATG? Sorry, ATG is 3000 into 440 divided by 1.25. Coming to TdB2, 0.9 into what is AVN? Again 7200 into 440 divided by root 3 into 1.25 plus what is ATG? 3000 area under tension into 300 divided by 1.10. Reverse, all values are getting interchanged, that's all. Okay, now 7000, sorry, we'll see first one. 7200 plus 300 divided by root 3 into 1.10 plus 0.9 into 3000 into 440 divided by sorry, what I have something I mistake it done. 7200 into 300 divided by root 3 into 1.10. So some value I got as 113.70 kilonewtons this value only, plus 0.9 into 3000 into 440 divided by, so this I got around 950.4 kilonewtons. Total I am getting here, it is 950.4 plus 1133.70, so 2084.1 kilonewtons. Okay, next, 0.9 into 7200 into 440 divided by root 3 into 1.25, so 1316.9 kilonewtons, only this term, plus 3000 into 300 divided by 1.10, so how much? 818.18 kilonewtons. Okay, so 1316.9 plus 818.18, how much you are getting? 2135.08 kilonewtons. Now out of this TD1 and TD2, this is the least. Okay, and what, due to rupture, this is one, and coming to here, it is 1165.909. okay, that is TDG 1165.909. next, TDN 1390.04 kilonewtons, and TDB equals to 2084.1 kilonewton. Now they asked the design tensile strength, right? The design tensile strength of tension member given tension member, what is that given? ISA 200 by 100 by 15 mm is least of TDG, TDN and TDB, right? That is equals to what? 1165.909 kilonewtons. Means this member can hold a tensile strength of 1165.909 kilonewtons. Okay, even though it takes much load, but what happens? We have to give, as per limit state, we have to give the minimum value as it's a maximum design tensile strength. Okay, so what we have seen today is, I will check it once again, this problem, very important. Okay, so a section is given, 200 by 100 by 15 mm section is given, and asked to find out what is its design tensile strength. So for that, what we have done, we have designed the section under what? Design strength due to yielding of gross cross section, then you got 1165.909 kilonewtons. Okay, and design strength due to net section rupture, then you got a value of 1390. Okay, and design strength due to block shear, you have calculated TDB1, TDB2, and you got the value of two values. In that, the least one should be taken. Okay, and out of these three, the minimum value is the maximum design tensile strength you are supposed to give the result. Okay, so I hope you understood all these concepts of tensile strength. That is problem on this one. So further we'll solve more number of problems. Okay, more number of problems you have to solve. These are only analysis. Some design problems will be there. Now we'll try to see what is the difference between analysis and design. Okay, that difference, if you know, it is very easy further. Okay, analysis and design, analysis problems and design problems. Simple thing. In analysis, section will be given. Section will be given. Now what this section will be given means, sectional details, like just now we have solved one problem, right? ISA 200 by 100 by 15 mm. That is the sectional details, means they are giving the section and they ask to find out what is its capacity. It's a design tensile strength. This is nothing but the analysis. Okay, in that all material properties will be given, that is weld connection strength will be given, material yielding capacity will be given, everything will be given, and section is given. You are ultimately getting how much its capacity, how much its capacity. Now coming to the design problems, what is a design problem means, here load will be given, load will be given. How this load are calculated means, from the structure where it is coming, they will be calculating the load. Suppose if I take a RCC, how the column load will be calculated means based upon the self weight of the slab and beams. Okay, and the load coming onto the beams all together will be transferred to the columns ultimately, right? So that is the reason first they will design the slab. Okay, then they will design the beam. Based upon those conditions, they will be designing the columns. From the columns, footings. Reverse process. Construction will be from the bottom to top, whereas designing will be from the top to bottom, right? So the design problem, load will be given. Now based upon the load, you have to choose the section. Now while designing, you have to do some assumptions. Some assumptions has to be done. What assumption you can do is, you have to take some strength of that material value, tensile strength. Load by strength is nothing what you will be getting area, because stress equals to load by area. Now I want area equals to what happens, load by stress. You have to assume this one. I want to make a use of so and so angle section whose strength is this much, whose stress is this much. Okay, it can bear a stress of this much. So for a particular load, how much load I have to keep means, suppose say 1000 kilonewtons, and I want to use a 300 Newton per mm square stress. So 1000 kilonewtons into 10 power 3 divided by 300, you will be getting how much, that 3333 mm square area. So for that, what you have to do, this is a design, right? You have to take some extra 10%. Okay, that is 1.1 into 3333. You will be getting some value. For that value, you have to choose from what, steel table. From steel table, you have to choose the value. Okay, you have to choose the section based upon this area what you arrived. After that, once you choose the section, remaining process will be same as what you done in the analysis. What you done, you have taken the section. Okay, you have calculated the gross area. Okay, Next, you have calculated the design strengths due to yielding of cross section, net rupture and block shear. Similar way you are supposed to calculate. Again, the least value should be there. After arriving the least design strength, suppose say for example again I got TDG. Whatever the value you obtained here, that should be less than the factored load what they have given. Suppose here it is 1000, right? Now 1000, consider this as a factored. Okay, that is a factored load. Now here whatever the load TDG you got, say something around 1200 kilonewtons, which is greater than 1000. So hence it is safe. If it is you are getting less than 1000 kilonewtons, this is wrong. The value you are getting here should be greater than the value they have given. Means you have designed, you have chosen by taking 10% extra. Okay. Now while choosing the section, you have to choose the section in such a manner that load carrying capacity should be more than the load given. So suppose if I got a minimum of 1200 from the three values, that is greater than 1000 kilonewtons, hence it is okay, means our section chosen is okay. If your value after arriving got less than 1000 kilonewtons, okay, after solve you have taken the section, you have calculated TDB, TDG and TDN, everything from the list you are going to choose. That least value should be higher than the factored load here given. If it is higher, the chosen section is safe. If it is lower, you have to redesign the section. So design problems are nothing but it's somewhat trial and error method. Okay, one or two or three attempts you will be getting the exact design values, right? Hope you understood this video. So further we'll try to solve the different number of analysis problems and design problems. Okay, thank you for watching.